Okay, let's dive into this. Welcome to today's Explainer, where we're taking a truly fascinating journey from the realm of abstract quantum physics straight into the massive, heavy-duty engineering of the MRI scanner. I mean, if you've ever looked at one of these absolute behemoths and wondered what on earth is happening beneath that sleek plastic exterior, well, you're definitely in the right place. Think of this as our engineering blueprint for building this machine from the inside out. We'll start with moving from theory to hardware, then check out the frozen superconducting magnet, look into shimming for perfect homogeneity, explore the RF coils, tackle gradients, noise, and eddy currents, and wrap it all up with the copper Faraday cage. All right, section 1, from theory to hardware. Let's make that jump into the physical world. Right away, we hit our first major, almost impossible engineering hurdle. How exactly do we trap a massive, unyielding magnetic field without completely melting the wires? Because, to get the kind of raw power we need for a clinical MRI, if you tried pushing standard electrical current through standard copper wires, it would generate so much friction and heat that the whole system would literally destroy itself in seconds. That brings us to section 2, the frozen superconducting magnet. This is the B0 field, the absolute beating heart of the MRI. To pull this off without melting everything down to slag, engineers use extreme cold. And I don't mean a harsh winter day. I mean 4.2 Kelvin. That is roughly negative 269 degrees Celsius. By bathing the coils in liquid helium to hit this temperature, the special niobium titanium wires actually undergo a phase change. They achieve zero electrical resistance. Zero. They become fully superconducting. But how do you keep liquid helium from just instantly boiling away in a cozy room temperature hospital? Well, the coils are housed in a cryostat. Our sources use a brilliant analogy for this. Think of it as a closed stainless steel sort of thermos, only it's way smarter than your coffee thermos. Modern scanners feature a mechanical cryocooler pump sitting right on top. So as the helium boils off into a gas, this pump continuously grabs it and compresses it back down into a liquid, keeping the scanner from running dry. In fact, some modern systems, like the Philips Blue Seal, use microcooling tech to operate on just 7 liters of helium for their entire lifespan. It's wild. So how do you even turn this thing on? You definitely don't just flick a wall switch. Engineers actually have to ramp up the magnet. They attach a power supply and literally pour thousands of amperes of electric current into the coils, carefully monitoring the field strength as it builds up. Once it finally hits the target, say a 3 Tesla B0 field, they throw what's called a superconducting switch. So the crucial point is, the power supply is then totally disconnected. Because there is zero resistance in those wires, that massive electric current just continues to flow in a closed loop, perpetually, without any external power source. It just goes and goes. Moving on to section 3, shimming for perfect homogeneity. Let's talk about balancing that massive field. A giant B0 field isn't very useful if it's lopsided. If you're wondering what the term shimming actually means, one of our sources hits the nail on the head with this highly relatable analogy. Ever eat in a cheap restaurant with like a wobbly table and you fold up like a matchbook to slide under the leg? That's a shim. In MRI engineering, shimming is exactly that concept, balancing out an uneven magnetic field so it is perfectly smooth and uniform across the whole imaging area. Engineers tackle this in 2 specific ways. First up, passive shimming. When the machine is first installed, engineers map the magnetic field and actually physically bolt little ferromagnetic pellets and metal washers into trays inside the bore. This subtly pushes and pulls the magnetic field lines into shape. Then there's active shimming. This uses specialized electromagnetic coils, mapped to complex mathematical shapes known as spherical harmonics, to dynamically fine-tune the field. And get this. Active shimming is done right before you are scanned. Why? Because the moment your physical body enters the scanner, you actually mess up that beautiful, perfectly homogeneous magnetic field. Section 4, RF coils, transmit and receive. Time to look at the mouth and ears of the MRI. These coils come in a few different flavors. Volume coils, like the classic birdcage design, surround a large area to transmit a broad, uniform radio frequency pulse. That's our B1 field. Then we have surface coils and phased array coils. These are the ones placed directly over the specific part of the body we're looking at. They act as highly sensitive antennas, just sitting there listening for the incredibly tiny RF echoes emitted by the protons inside you as they relax. But here is a massive engineering catch. The transmit pulse is incredibly powerful, while the receive echo is incredibly weak. If those ultra-sensitive receiver coils were turned on during the massive transmit pulse, they would be instantly destroyed, and worse, the patient could be severely burned. No thanks. To prevent this, engineers use something called coil detuning. They utilize pin diodes. Think of them as ultra-fast electronic switches to rapidly break the circuit of the receive coils the exact millisecond the transmission happens, and then instantly reconnect them to listen for the echo. It is an absolute masterpiece of nanosecond precision. Section 5. Gradients, noise, and eddy currents. The muscles of the scanner. So, the gradient coils inside the scanner have to switch on and off incredibly fast to encode spatial data, but doing this induces what are called eddy currents. Basically, these are unwanted, rogue electrical currents that get created in nearby conductive materials, like the cryostat itself. And the problem is, these eddy currents generate their own unpredictable magnetic fields, which distort our carefully shimmed main field and cause all sorts of nasty image artifacts like shearing, shading, and ghosting. To stop these eddy currents from completely ruining the image, the hardware uses two really clever tricks. First, active shielding. They place secondary coils outside the primary gradients, running the current in the exact opposite direction to trap and cancel out the escaping magnetic flux. Second is pre-emphasis. This is more of a software trick, where the system intentionally modifies the input current to the gradients, essentially distorting it on purpose. That way, when the eddy currents inevitably interfere, the resulting magnetic field balances out to be exactly what we wanted in the first place. Now, what's really interesting here is the acoustic noise, because those rapidly switching gradients experience massive Lorentz forces. We're talking about magnetic fields violently pushing and pulling against the wires themselves. They literally vibrate and bang against their mountings, which creates that deafening techno-beat noise MRI machines are so famous for. To fix this, they add physical retrofits. Just adding a heavy 20mm ceramic absorber to the bore can drop the volume by almost 11 decibels. That is a game changer for making the experience way more comfortable for the patient. Finally, Section 6, the copper Faraday cage. Let's zoom out to the architecture of the hospital room itself. See, the MRI signal we're trying to read is so incredibly weak that a local radio station, a passing elevator, or just someone's cell phone in the hallway could completely ruin the image. To stop that, the entire scanning room must be converted into a Faraday cage. Our sources describe this beautifully as a mesh umbrella for electromagnetic radiation. It shields the inside from the outside and protects the outside from the inside. But building this is a serious architectural feat. The entire room is literally lined with high-purity copper or aluminum panels, perfectly soldered together. The heavy doors use these special beryllium copper contact fingers around the edges to ensure complete electrical continuity without a single microscopic gap when they close. Even the air conditioning vents and medical gas tubes have to pass through specialized honeycomb waveguide filters that physically block radio waves from sneaking in. If even one tiny gap exists anywhere in that room, the whole cage fails, and your multi-million-dollar MRI machine is essentially useless. Which leaves us with this final thought to ponder. How exactly do we balance delicate quantum spin, extreme freezing temperatures, and heavy room-size architecture all at once? An MRI is just so much more than a giant magnet. It's this stunning, highly calibrated intersection of abstract quantum physics and heavy brute force medical engineering, all working in perfect harmony, just so we can peer inside the human body. Think about all that engineering the next time you're lying in one, hearing that loud thumping beat. Thanks for joining me on this explainer.